Okay, so this is a video solution for the quiz we had today. And so I want to kind of go through some of the basics of how you do these problems. Okay, so here we're given a hypothesis test, and we're told the z-statistic, and we want to find the p-value. So all we do is we simply use the z-score, and we find the probability in the tail. Okay, so we go ahead and do that, and I'm just going to use StatCrunch. So what we know here, remember what a z-score is. So for the first problem, remember that a z-score comes from a standard normal. Okay, so we have a particular z-score here that has a value of, where is it? Oops. 2.19. Okay. So this means that I'm taking the probability in the tail. This is going to be the p-value. Okay? And again, when you're looking at z-scores, it's the same as a test statistic. Okay, so remember that in this case, the alternative is that we want to see if the mean is greater than a value. In this case, it's 90. Okay. So this means that if we were looking at x bar, we'd be testing the upper tail, right? Because the inequality is pointing towards the upper tail. That's where the p-value would be. Well, the same is true for the z-score. Whatever is true for x bar is true for the z-score. So again, we're going to test the upper tail, and that's why I'm taking the p-value as the probability in the tail. So now we go straight to StatCrunch, and we just compute that p-value. Okay. All right. So I go to Stat Calculator. Oops. Normal. A mean of 0, standard deviation of 1, and I want the probability that I'm greater than 2.19. And I just compute this in StatCrunch, and there's my answer, and I can go back and just cut and paste this. Right? And it wants it rounded to 3 decimal places, so I'm just going to round that off. So this would be 0.014. Okay. And so now we want to try to interpret this. So remember what the p-value is. The p-value is the probability we could see the test statistic if the null hypothesis was true. So if the null hypothesis is true, which means that mu has to be equal to 90 degrees, it's the probability that I would see a score, a z-value of 2.19 or higher. So to kind of go back why that's true, remember what the p-value is. This is the distribution of the z-scores if h0 is true. Okay, if h0 is true, these z-scores come from a standard normal. And h0 is true, reduces down to mu equal to 90. Okay. And there we go. All right. Problem 2. So if a hypothesis test were conducted with alpha equal to 0.01, for which of the following p-values would the null hypothesis be rejected? Neither. Okay, remember what the decision rule is here. So for problem 2, the way we make our statistical decision is if the p-value is less than alpha, then we reject h0. So the way sometimes people say this is a little rhyme. When p-value is low, h naught must go. In other words, when the p-value is low, it's less than alpha, h naught must go. Okay. So if we go back to this, we know that it has to be this, that we're going to reject the null hypothesis. I'm sorry, I didn't realize this, sorry. When the p-value is 0.006, we are less than. So we're going to reject the null hypothesis because we're less than the value of alpha. So let's just kind of go back and look at this. So for part A, the p-value in my problem was 0.006. So 0.006 is less than 0.01. So therefore, we're going to reject h naught. Okay? Here, 0.02 is not less than h1, so we're not going to reject it because the p-value is not less than alpha. Okay, good. Okay. So which hypothesis, the null or the alternative, is the status quo? The null hypothesis is always the status quo. The alternative is the research. So the way we think of this is the alternative is what you're trying to prove. In the absence of any evidence, we believe the null hypothesis. So if you go back to this chord analogy that I was talking about, the way we think of this is the following. The null is basically what we come in believing, or we could say not guilty. I shouldn't say innocent. What you're trying to prove is the prosecution. Okay? This is the status quo, meaning that if no proof is brought, if the prosecution doesn't present any evidence, this is what we believe. This is the status quo. Okay. Okay, so this is a long word problem. So some sort of acid is a chemical used in products that coat cookware to prevent food from sticking. That's kind of sad. An agency is investigating the potential risk as a cancer-causing agent. Yep. It's known that the blood concentration of this chemical in the general population has a mean of 6 parts per billion and a standard deviation of 10 parts per billion. Okay. An article reported on tests of this exposure conducted for a sample of 33 people. All right. And so we want to know what is the probability that the average blood concentration is greater than 7.55 parts per billion. Okay, so we're going to go back and kind of look at this. What we know is that the sample means come from a normal distribution. So this is important. Whenever we're looking at sample means, okay, it's important to know that X bar has a normal distribution. Okay, the mean of X bar is equal to the mean of X, which is mu. The standard deviation of X bar is equal to the standard deviation of X divided by the square root of n. So this can be S or sigma for our purposes, divided by the square root of n. So in this problem, what do we know? Okay, we know that the mean is 6 parts per billion, and we know that sigma is 10 parts per billion, and we know that n is 333. So that lets me figure out what the distribution of X bar is. So X bar has a normal distribution its mean, which sometimes we write like this, the mean of x bar is equal to mu, which is equal to 6, and the standard deviation of x bar is equal to the standard deviation of x divided by the square root of n, which is 10 divided by the square root of 333. And so you go ahead and just put this in your calculator, right? So 333 square root 1 over times 10. And it's going to be roughly, 0.548, right? 0.548. Okay, so now I know everything I need to know. This is just a regular normal distribution problem. I know the mean of the normal distribution. I know the standard deviation, so I can compute any probabilities I want. So here they want the probability that I'm greater than 7.5, so I can compute that. I can just go into StatCrunch, right? So if we go into StatCrunch and say this is 6, this is, what do we say, 0.548, oops, right, and let's make sure we do this right here, and we want greater than 7.5. And let me make sure I had a standard deviation correct, 0.548, yeah, okay. And now I'm ready. And that's my probability. So it's 0.00309, okay? Okay. So this is the probability. It's what's in the tail. All right. And now they say, okay, what actually happened was the true mean was 300 from the sample. Use this information to make an inference about the true mean of the population. Well, what we know is that mu should definitely be greater than 6, okay? In other words, if I'm testing now, I'm going to be testing to see, since this is so large, I'm going to be testing to see if it's greater than 6. Okay. All right. I'm going to stop here and break up the video. So I'll make the next part of the video over. No, you know what? I'll just keep going on. I think this. I'll do it in 2 parts. Okay. The average salary for a certain profession is 98,000. Okay. Assume the standard deviation is 30,000. A random sample of 55 people. Okay. So again, let me just kind of flow this out. Okay. So here, what I know is I know that the mean, so x is a random variable, the mean equals 98,000, right? The standard deviation is 30,000, and n is 55. So the central limit theorem tells me that x bar will have a normal distribution. The mean of x bar will be equal to the mean of x, which is just 98,000. And the standard deviation of x bar, we're going to write sigma with an x bar as a subscript, is just going to be 30,000 divided by the square root of 55. And we can go ahead and compute that out. Oops. it's going to be roughly $4,045. And we'll round this off just to regular, so that it makes sense. 4045, and if we round this off on cents, it'll be 0.20. Okay? So now I'm ready to answer all the questions. I know everything I need to know about x bar. So the mean of x bar is going to be the same as the mean of x, which is 98,000. Standard deviation of x bar we just worked out. It's going to be 4045.20. Okay. We know that it's normal because we have over 30. And we could compute the z-score, right? So we could go ahead and do that if we wanted to. So we know that if we had x bar equal to 90,000, and it comes from a normal distribution, how do I find the z-score? Subtract off the mean and divide by the standard deviation, right? So this would be x bar minus mu of x bar divided by sigma x bar. Okay. Or in other words, 90,000 minus 98,000 divided by 4045.20. And we can go ahead and compute that out really quickly here. I'm just going to take the reciprocal of this and multiply it by 8,000. Okay, and change the sign. I can't do that here, that's okay. So the z-score is going to be roughly minus, rounded to 2 decimal points, minus 1.98. Okay. The probability that x bar is greater than 90,000, I can do that with the z-score. I can do that in StatCrunch. I'd rather do it in StatCrunch. Okay. Oops. So the mean is 98,000. We said the standard deviation was $4,045.20. And we want to find the probability that we are greater than 90,000. Okay? And that should do it. And notice it's very large. Okay, not surprisingly. So it's going to be roughly 97.6%. So to 3 decimal places, that'd be 0.976. Not sure why that happened. Okay, 0.976, and that should be it. Okay. One more and then we'll split it in 2. What is the level of significance of a test of hypothesis? Okay. So alpha is the probability of committing a type 1 error. All right. Remember what it is. It's the probability of a false alarm, saying that something is true when it's not. That's a type 1 error. So we can automatically only look at the alphas here because level of significance is alpha. It's type 1 error, so these are all saying, so B, D, and E are all out because the level of significance is alpha, not beta. Okay? C is out because it's not a type 2 error, it's a type 1 error. And a type 1 error is rejecting the null when in fact it's true. So if you're not sure about this, go back in the book and read about type 1 error and type 2 error. Okay. All right. In the test of the hypothesis, the null hypothesis is that mu is equal to 10 versus the alternative is not equal to 10. We have a sample of 50 observations, and the sample mean is 10.7 and the standard deviation is 2.7. Okay, so we want to find and interpret the p-value. So first we want to get the p-value. So let's kind of look at what's going on. Okay, take this apart. Okay. So the null is that mu is equal to 10. So this is my mu naught, right? And the alternative is that it's not equal to 10. All right. If H naught is true, then X bar comes from a normal distribution with a mean of 10. That's what the null hypothesis says. And the standard deviation is whatever the observed standard deviation is divided by the square root of n. And I'm going to go ahead and compute this value out because we're going to need it later. Okay, so this ends up being 0.3818. So now we know everything we need to know about X bar, right? We know that it has a normal distribution. We know that since we're supposing the null hypothesis is true, the mean is the same under the null, 10, and the standard deviation is going to be 0.381837. And I'm just being on the safe side by putting a lot of decimal points in, okay? All right, so now we can answer some questions. So what is the p-value? Well, remember, our observed value here was 10.7, right? So the X bar observed was 10.7. So I'm going to compute the probability in the tail, right? So my distribution of X bar under the null hypothesis looks like this. Here's my value, 10.7. The probability in the tail, I'm going to have to multiply it by 2. That's going to be the p-value. Okay? Because why? Because I'm looking at both tails when the alternative is that they're not equal. Okay? I'm computing the probability in both tails. Okay. So let's go ahead and compute the probability in the one tail first. Okay, so I know this will be 10.7. That's my test statistic. The mean under the null hypothesis is 10. And this was, let's see, 0.3818. 0.381837, right? Make sure I put a decimal point in front of there. Okay. Let's just check it real quick. 381, yeah, that looks good. Okay. Now, I need to multiply it by 2. So 2-tailed, that's when the alternative is I'm testing it's not equal. I'm testing both tails. So 2 tails means I multiply this by 2. So I'm going to have, how many decimal places do they want? 4 decimal places, okay. So let's go back to this. I'll clip this out. And I'm going to multiply that by 2. So this will end up being just to be on the safe side, 0.33382322. Okay, so that's my p-value. Very, whoops, I did something wrong, sorry. 0.033382322 times 2. There we go. Okay. So my p-value is going to be roughly rounded to 4 decimal places. So it'll be 0.0668, right? Go ahead and enter that. And what do we decide? Well, notice that if I compare it to 0.15, p is less than alpha, right? So we would reject it if this was our alpha, right? If alpha I'm sorry, there would be sufficient evidence, sorry. So notice that for any alpha greater than 0.07, there'd be sufficient evidence to reject. Okay, if alpha was larger than 0.7, p would be less than alpha, and we would reject, all right? This isn't correct because in this case, p would be less than alpha. There'd be sufficient evidence to reject. Here also this isn't correct. If alpha was less than 0.07, okay, then we wouldn't reject. P would be greater than alpha. Okay, there wouldn't be sufficient evidence to reject. Okay, I'm going to break the video probably in two because this is going to get a little too long otherwise.